Next, I'd like to talk to you a little bit about reactions called reduction-oxidation reactions, or redox reactions for short. Now, these are very important reactions as well in chemistry. They occur in all different types of reactions, with one exception. We won't see reduction-oxidation once we learn what it is. We won't see it with those types of reactions we call double replacement, which you may have seen as when ions just kind of switch ionic partners, ionic square dancing, I like to call it. We won't see it in those. But for all other types of reactions like synthesis, decomposition, single replacement reactions, or combustion reactions, we'll always see reduction-oxidation occurring. So let's talk a little bit about what that means. One of the assumptions we need to make, okay, and this is a little bit of imagination required here, is we're going to look at all of the compounds or all the substances that we use in reduction-oxidation reactions as being ionic, even if you know in the back of your or the front of your mind that the compound you're looking at is actually covalent. With reduction-oxidation, I like to tell students, just forget that there's anything such as covalent bonding. Everything is put together plus and minus like ionic compounds are, even if it is, wink wink, truly covalent. Okay, so everything's going to be ionic. And what we're going to do, since again everything is ionic with reduction-oxidation reactions, what we're going to do is, using our periodic table, and a periodic table that has all those different charges for all the different elements. You may sometimes have asked, what charge do I use? And your teacher probably says, use the top charge. With reduction-oxidation reactions, we get to use all the available charges on the periodic table, whichever one works for us. Not any charge, the one that works for us. But now it's wide open. So we're going to assign a charge, either positive or negative, to every element that we see in our chemical reaction. That's important, element. Okay, so make sure that every element gets a proper charge. Again, with ionic compounds, what's the basis? We want to make sure the plus and minus charges add up to a net sum of 0. Okay? And whatever charges we need to use, we'll assign them that charge to each element. What we're going to be playing is, just like we saw with weak acid-base reactions in a previous video, a little bit of ping pong. But in this case, we're going to be playing electron ping pong. So electrons being pinged and ponged back and forth. The problem is, the ping pong ball, the electron, is so darn tiny that we can't see it written in a chemical reaction. What we have to do is just look for who changes their charge from one side to another, from reactant side to product side. So that's exactly what we're going to do. And that'll tell us who's gaining electrons, who's getting rid of electrons, who's getting electrons. Okay, by the charge change from one side, the reactant side, to the product side. Now the rules are, and I'll leave this up here, we'll refer back to it. What we want to look for from reactant side to product side is how the charges are changing on what? On each element. If we see that the charge is increasing, so if we see an increasing charge, that means that the element is technically losing electrons, because electrons have a negative charge. If we see an increasing charge, we call that oxidation. Okay, so if the charge goes up, say from 0 to +2, or from +1 to +3, that's oxidation. Okay? The opposite case would be if the charge is decreasing. So if we see a decreasing charge, and this one makes more sense to me, really, a decreasing charge, say from +2 down to -1, or +3 down to 0. Okay, if the charge from reactant side to product side is decreasing, going down in value, that's called reduction, which again sounds proper because it's being reduced in value. Okay? All right, so let's look at some examples using these general rules, okay, and these guidelines for reduction-oxidation reactions. Let me just clean up the board here, and I'll leave our rules, I guess you could say, up here for us to go by. Okay, let's take a very simple chemical reaction. You've seen this one before, probably. CH4 plus O2 reacts to form CO2 and H2O. You might recognize this as a combustion reaction. Okay, a combustion reaction is a reaction where something, a fuel, is being combined with oxygen and burning. Okay, this is natural gas in this case. And we want to see the reduction oxidation process that's occurring. So remember, one of the rules that we had up here was to assign a charge to each element, because we're pretending that every compound up here is ionic, put together plus and minus. I chose this one first because in reality, none of these are ionic compounds. These are all covalently bound atoms forming covalent compounds. But again, we pretend that everything's ionic. Okay, so referring to your periodic table, and you really want to have your periodic table handy for this. Let's look at the first compound. Well, remember with ionic compounds, the first charge that we see is always the positive charge, and then the second is the negative. It's always in that order, positive and then negative. So let's assign some charges here. And sometimes it may be useful when you have a variety of charges, like I believe carbon can be +4, +2, -4, or something like that. If you have a variety of charges, leave that one and we'll come back to it. Here we see hydrogen in the what seat? The negative seat, because it's in the back. Okay, positive, then negative. So hydrogen is the negative ion. And if you refer to your periodic table, hydrogen's negative options, there's only one. -1. So let's assign a -1 charge here to the hydrogen. Well, if each hydrogen, and there's 4 of them, okay, there are 4 of them, each hydrogen here has a -1 charge, that's a total charge of what? -4. So what charge must we assign from the options for carbon for a positive charge to add up to 0 with the negative ion? Well, carbon does have the option of being +4. And there's only 1 carbon in the formula. So 1 carbon with a +4 charge combined with 4 hydrogens, each with a -1 charge, that adds up to 0. So we've properly assigned the charges for this compound. Again, remember, it's really a covalent compound, but here we're assigning charges to it. Now here's something neat about reduction oxidation reactions. Elements that are by themselves, okay, although this oxygen here is paired with itself, but with no other element involved, when we have a lone element, these are very easy to assign. We simply assign them a charge of 0. Okay? So oxygen on the reactant side gets assigned a charge of 0. Let's go to the product side and identify the charges that we see. Okay, and then we'll start looking at changes. Okay, we have carbon again, and now with oxygen. Now here oxygen is in a compound. So it's not going to be 0 like it was over here when it was alone. Now it's in a compound, and we need to look at the possibilities for oxygen. Again, I think oxygen is the easier one to do here. Oxygen only has, as far as I know, 1 possible charge available for it when in a compound, and that charge is -2. Okay, I believe every periodic table I've ever seen only has a -2 possibility for oxygen. But remember, there are 2 of them here. So 2 oxygens, each with a -2 charge, gives us a total of -4 charge. Okay, so what must the carbon be? Well, the carbon is still going to have to use that +4 charge to add up to 0. Okay, because again, there's only 1 carbon here. Okay, so we've identified the charges in the compound carbon dioxide here. Let's look at the last compound, water. And we have hydrogen out in front now. Hydrogen is in the positive seat. Oxygen is again in the minus seat. Let's do oxygen first. It doesn't really matter in this case. Oxygen we know is -2. And what possible positive charges do we see listed on the table for hydrogen? Over here we saw it as -1, but that's because it was in the minus position. Here it's out in front, so it must have a positive charge, and the only positive charge possible for hydrogen is +1. And that will add up to 0 in this compound. +1 2 times is +2, and when we add it to the -2, we get a net charge of 0. So we can see, just going back to the beginning, that here, with the 3 compounds at least, the net charge adds up to 0. -1 4 times, added to +4 gives us 0. +4 and -2 2 times would be -4, so +4 and -4 gives us 0. And then +1 2 times, added to the -2 also gives us 0. So we've properly assigned the charges to all the elements, okay, each element. Now we get to look at what happened from one side to the other. Okay, so let's just take one element at a time. And let's do the carbon. Let's look at what happened to carbon from reactant side where it was +4 to product side where it was, well, it is still +4. So nothing happened, and that'll often be the case. You'll usually have one element that doesn't change. Okay, so in this case, the carbon was neither oxidized nor reduced. It stayed the same. Its charge did not change from one side to the other. So let's leave carbon for the moment. Let's look at hydrogen, just going in order here. Hydrogen on this side had an assigned charge of -1. If we look at the other side, hydrogen has an assigned charge of +1. So just think, on the number scale, -1 to +1, and it doesn't matter how many jumps it made, it went up, didn't it? -1 to +1 is an increase in charge. What does an increase in charge indicate? That element underwent what we call oxidation. And really what happened is the hydrogens here gave up some electrons and ended up with a more positive charge. But just look at the charge from one side to the other. Okay, the last element we need to look at is oxygen, and let's see what happens. Oxygen here had, on the reactant side, had an assigned charge of 0, again, because it was all by itself. On the product side, oxygen actually shows up in a couple different places, doesn't it? So it goes from 0 on this side to here and also here. But in both cases on the product side, it's -2. So 0 to -2 on the number line would be going in what direction? Down, a decrease in charge. A decreasing charge indicates reduction. Okay? So in this reaction, the element oxidized, or the element that underwent oxidation, is the hydrogen because its charge changed from -1 to +1 from reactant side to product side. And the oxygen went from 0 on the reactant side to -2 on the product side, so its charge went down, it was reduced, it underwent, in other words, reduction. The carbon, remember, wasn't changed. Okay, it was +4 here and also +4 on the product side. Okay? And what we've done there, what has happened in the reaction, is some electrons have been, they're being juggled in a sense and made available to the atoms to increase and decrease their charge. Let's look at another reaction. And let's take magnesium nitride plus chlorine, and let's get the products here. We would get magnesium chloride and nitrogen by itself. Okay, and let's assign some charges to this, and then we'll look again what happened from reactant side to product side. Okay, now everybody in my classes always wants to assign a charge to nitrogen because there's a whole laundry list of charge possibilities for nitrogen. That can be a little tricky though. So instead of trying to assign a charge right away to nitrogen, let's look at the magnesium here, which is an alkaline earth metal, which only has one possible charge listed on the periodic table. And the only possible charge on the periodic table for magnesium is a +2 charge. Okay, now there are 3 magnesiums in the formula, but each one has a +2 charge. So what does that mean for the total positive charge in this compound, magnesium nitride? +2, 3 times, +2, +2, +2 would be +6 total. Okay, let's do a little scratch work down below. This side is +6. That means this side has to be -6 to add up to 0. But we have how many nitrogens here? There's 2 nitrogens. And if those nitrogens are adding up to a total of -6, then what charge must we assign to each one of those nitrogens, again, from the list, to add up to -6? Well, it would be the -3 charge because, again, we have 2 nitrogens. -3 and -3 again would give us -6. Okay? So those are the proper charges for those 2 elements. at the beginning of our reaction. Here we have chlorine. Again, it's a diatomic element, so it always comes in pairs, but it's not in a compound. It's not with any other element, so we simply can give it a charge of 0, which again is nice. Let's look at the product side. Here again we have magnesium. Magnesium, the only possible charge, and these are the ones to focus on first, is a positive 2 charge in this compound. Chlorine, I believe, has several charges, but in this case, in order to add up to 0, the charge we must use, we know it's going to be a negative charge because it's in the negative position. The negative charge needed for chlorine, since there are 2 of them, a negative 1 charge would add up to 0 with the magnesium's positive 2 charge. There's 2 chlorines, each one at -1. That's the proper charge for the chlorine. And then what do we have at the end here? We have nitrogen, all by itself. What do elements all by themselves get a charge of? Simply 0. Okay? And that's, again, the first thing you want to do is go through carefully assigning a charge value to everybody in the reaction, every element. Now, we get to look at what happens from one side to the other. And let's just go in opposite order this time. Let's look at the chlorine first. Chlorine from reactant side here to product side, what did it do? It went from a charge of 0 to a charge of -1. So what happened to its charge? 0 to -1 is getting smaller, or it's being reduced. So we say that the chlorine underwent reduction. The element chlorine was reduced. Okay, and then just working our way backwards here. Nitrogen goes from -3 on the reactant side, the charge we assigned it, and shows up on the product side as 0. So what happened there? -3 to 0. -3, -2, -1, 0. It actually increased, didn't it? An increase in charge, in this case from -3 to 0, that is a sign of oxidation because the charge is increasing. According to our rules here, an increasing charge indicates oxidation. Okay? What about the magnesium? Well, the magnesium, let's see, I'm running out of room here. Let's do it up here. Was +2 on this side. On the product side, it shows up also as +2. So nothing happened, just like I think the carbon in the first reaction. Okay, so no change here on the magnesium. It was neither oxidized nor reduced. But the other elements were. Let's do one more example. We'll take kind of a simple one here. Let's take N2 plus H2. I say a simple reaction, but a very important reaction, producing ammonia. Okay? Only 2 elements here, so not a lot of legwork involved. And in fact, on the reactant side, what do we have? We have 2 different reactants. Each one of them are simply elements. They are not in compounds. So we simply assign them both a charge of 0. Okay? Well, on the product side, what do we have? We have ammonia, which is truly a covalent compound, but not in reduction oxidation. We consider it an ionic compound put together plus and minus. And let's assign the proper charges here. Again, nitrogen has such a long laundry list of possible charges. You may want to wait on that one. Let's look at hydrogen sitting here in the minus position. Again, what options do you have for hydrogen having a negative charge? I believe your periodic table will only allow you to assign a -1 charge if hydrogen is in the negative position. -1 how many times though? 3 times. So it's a total of -3. So what must this one nitrogen atom have for a charge? Well, it must be positive in the first place, but also the numerical value is going to be +3. Again, to add up to 0 with the hydrogen atoms. Okay, so not too tough there to assign the possible charge, the proper charges rather, from our possibilities. And let's see what happens from one side to the other. The nitrogen over here on the reactant side was 0, and when it shows up on the product side, it's positive 3. So just a little bit of scratch work here. 0 to positive 3, that is what? That's an increase in charge. An increasing charge is an indication of oxidation. So the nitrogen was oxidized from reactant side to product side in this reaction. The hydrogen, the other element, the only other element, was again by itself on the reactant side, so it has a charge of 0. And when it showed up on the product side, lo and behold, it has a charge of -1, so it went from 0 to -1. Not a major change, but a decrease in charge nonetheless, and therefore the hydrogen was reduced, okay, and underwent what we call reduction, which again makes more sense. When the number goes down charge-wise, we say that element is reduced. And you can try this for all your reactions. Assign charges. Again, you have to pretend sometimes that you're dealing only with ionic compounds, even if you have covalent compounds. These were all covalent compounds, okay, with compound and 2 covalent species over here. But we pretend with reduction oxidation that everybody is ionic, and we get to assign these charges and see what happened to the charges from reactant side to product side. The only reaction you won't see this with, again, are those double replacement reactions where the charges actually remain the same from reactant side to product side.